Today, we are going to introduce a supermodel in the field of video generation called LTX2, also known as LTX-Video. So, how powerful is this model? First of all, it is open source. Additionally, it can simultaneously generate video dialogue, sound effects, and background music. It also supports video-to-video generation using Canny, depth, and pose controls. Another major feature is that it natively supports video upscaling and enhancement. This means the efficiency of video generation is extremely high. Currently, the official ComfyUI team has already provided native support for this model. You can find relevant information on the official ComfyUI blog. Right now, the downloadable workflows available include text-to-video, image-to-video, and video control workflows using depth, pose, and Canny models. You can download these workflows and drag them directly into your ComfyUI to run them. There's another way to access them. You can update your ComfyUI to the latest version, then click on Templates, select Video, and in the download list, check LTX-Video. At this point, you will see the text-to-video workflow, the image-to-video workflow, and the workflows using ControlNet to drive video generation. Regarding model downloads, after clicking on each workflow, there is a very detailed explanation on the left side. This includes download links for the main model, text encoders, LoRa's, and other necessary models. It also clearly explains the local directory structure where these models need to be stored after downloading. I have built these workflows on Running Hub so you can access the platform through there in the ComfyUI space. Running Hub is a fantastic online workbench because they follow up immediately whenever new models or extensions appear. You can register for Running Hub using the invitation link in my video description to get 1,000 free credits. Plus, you get an extra 100 credits gifted every day you log in, so you can easily test your own workflows. In this video, we will explain 5 specific workflows in detail, covering text-to-video, image-to-video, and using ControlNet, Canny, pose, and depth to drive video generation. Let's start by looking at the simplest text-to-video result. Here is a prompt describing a researcher pressing a red button, which then detonates an unknown device. Let's look at the final generated effect. Note that this generation comes with its own background music and sound effects. Let's listen.
May they forgive us.
Looking at the result, the quality is very high. The current resolution is 1280. However, this workflow is relatively complex. So when analyzing it, you need to have a clear mental map. Please note that this workflow is divided into 2 parts. The first part is the stage 1 sampling, which is mainly responsible for generating the base video. The stage 2 sampling is mainly responsible for upscaling. Most of the subsequent workflows follow this exact structure, and the composition of the upscaling sampling workflow is basically the same across them. The most critical part here is actually the latent generation. So, focus on these 2 points, the 2-stage sampling and the latent generation when trying to understand the workflow. Let's break it down one by one. First, let's look at loading the main model. We use the standard 3 components here. We specify the main model via a variable. This is the LTX2 main checkpoint, specifically the FP8 version. As per the instructions on the left, this model goes into the checkpoints folder. Therefore, we use the load checkpoint node, not load diffusion model, because it includes a built-in VAE. You might ask, why are you loading another VA here? This brings us to the second crucial point. You must realize there are 2 distinct pipelines in this workflow, one for video generation and one for audio generation. This is quite different from traditional models. The standalone VAE we are loading is actually an audio VAE encoder, while the video VAE encoder is inside the main checkpoint. Next is the most important part, understanding the latent generation mechanism. There is a specific logic here. First, we generate an empty image with a resolution of 1280 x 720, which is our final target resolution. Now we need to scale it down to half its original size. Why? Because although our final output is 1280, we go through a round of upscaling using a 2x upscale model. So, as a reference for the auxiliary latent generation, we first scale it down by half for the stage 1 sampling. Next, we get the width and height and set the total frame count, which is 121 frames here. Then we generate the latent. Remember what I reminded you, LTX2 has 2 tracks, audio and video. So, there are 2 latents. We use a node to create an empty video latent and another for an empty audio latent. We then combine them below that are our prompts. We use the LTX-V conditioning node to generate positive and negative conditions. Next is the stage 1 sampling. We use an advanced sampler. The seed is currently fixed, but you can set it to randomized. We set the CFG value to 4.0, so the negative prompt is active. We have our sampler, and below that, the sigma. Seeing this node, you should know why we use an advanced sampler. This is an LTX-V exclusive scheduler, so we must use this specific node to generate a sigma to feed into the advanced sampler. After sampling, we must execute a latent split operation. The purpose is, of course, to separate the audio and video before proceeding to stage 2. In stage 2, we use a distilled model, obviously, to speed up sampling. Here, we use a standard 2x upscale model. You don't need to specify the magnification factor. It defaults to 2x. We take the latent generated from the first time, process it, and sample it again. This second sampling differs slightly from the first in 2 places. First, the CFG is set to 1.0 because we are using a distilled model. Second, in stage 1, the sigma was generated by a specific node, but in stage 2, the sigma values are set manually. Note that before sampling this latent, we need to merge the audio and video again. After sampling, we split them once more and decode them separately. Finally, when saving the video, we feed them into their respective inputs to get our final result. I think LTX2 performs remarkably well in text-to-video, so I ran a few more tests. The second workflow shows a dreamy bridge scene at nightfall. As you can see, the quality is very high. The third one is a character video. In the prompt, we describe a person whispering, "I miss you" with a sad expression, and then saying, "I hope you are doing good." We want to focus on whether the voice settings work.
I miss you. I hope you are doing good.
The key audio content described in the prompt is displayed very well here. For the fourth example, I tested a non-realistic scene. Look at this room with several frogs. I also included some dialogue design. Let's listen.
One with the mud. We are one with the flies.
You can hear that the scene design is very interesting. These 4 examples are enough to show us the power of this model. Now, let's move to the image to video section. The workflow is largely the same as before. The only difference is in the latent generation. Let's take a quick look. We have a reference image. We scale it to 1280 x 720 RSet resolution. Then, just like before, we get the image size, generate an empty image, scale it down by half, and create an empty video latent. The most critical node in the entire image to video process is right here, image to video in place. This essentially injects the information from our reference image into our latent. Here we need to pre-process the reference image. We scale it by its longest side to 1536, compress it, and then use this image as a reference for the latent, injecting it via this node. The rest of the content is basically the same. Let's look at the prompt. It is very simple. A beautiful Western woman with long hair. She laughs heartily first, then suddenly turns serious and says, "It is a secret." Let's see the final result.
It's a secret.
The effect is truly amazing. It reflects our prompt so precisely, both visually and audibly. Achieving such a good result is, I think, quite astonishing. Now we enter the third part. You can think of this as video-to-video generation, but we utilize mechanisms similar to ControlNet to control the final video generation first. Let's look at depth. I have a previously generated video of a bartender drinking red wine. The workflow is similar to the previous ones. The main difference, again, is in the latent generation. First, we acquire 121 frames from the video because that is our target length. We set the resolution to 1280 x 720 and scale it down by half. The key step is generating the depth map. There are many ways to do this. Here, we aren't using a standard ControlNet preprocessor. Instead, we generate the depth map through sampling using a model called Lotus. You can find detailed download and path information in the notes. Since this is a standard SD model, we use the SD 1.5 VAE. After sampling, we get a depth map. However, this depth map is currently inverted. If we want to use it, we must flip it. Black becomes white, white becomes black. So we pass it through an invert image node. After that, we have our control video. We connect this control video to a node called LTX-V add guide. This adds the control signal. Just like before, we generate an empty video latent and an empty audio latent. We then add the depth control signal into this latent and proceed with the subsequent sampling. This is the basic mechanism for implementing ControlNet here. Regardless of the control type used later, the basic logic remains the same. Let's look at the result. Since I used the same prompt as before, the girl laughing then saying it is a secret, the action follows that. However, you will notice that the aesthetic quality of the human figures generated by LTX-V is open to debate. Next, let's look at the Canny outline part. Similarly, we have a reference video of a beauty smiling. We generate 121 frames at 1280 × 720. Here, we use a very simple method to get the outline map using the Canny processor. The logic below is basically the same. We generate the important latents, then use a node similar to image to video to inject our contour map signal into the latent. Note that the image we inject is the first frame we acquired. To add the full control signal, we again use the LTX-V add guide node. Just like with the depth map, why operate this way? We don't need to dig too deep. We are following the official setup. We just need to explain its rationality. After that, we go through stage 1 and stage 2, sampling to get the final result. Again, look at the result. The aesthetic appeal of the character isn't great. Also, please note that this workflow is one I fixed myself. The original official workflow wouldn't run because the node was empty and unconnected. I assume the officials will fix this later, but the general logic remains as shown. Finally, let's look at post control. The basic idea is the same. The original video hasn't changed. We use DW OpenPose to acquire the post map. The key is still the latent generation using LTX-V add guide to add the control signal before sampling. Since the model doesn't generate very good looking people by default, I changed the prompt here to a 40-year-old man. The final result looks like this, quite dorky and cute, right? So those are the 5 workflows we analyzed today. In these workflows, pay attention to these points. It uses a 2-stage sampling process. All generation is split into 2 lines, video and audio. Master the methods of latent manipulation. If you grasp these, you will be able to clearly understand the workflows for any generation scenario, whether it is text to video, image to video, or video to video. Overall, there was a lot of content in this video. Go ahead and try it out yourself. That's all for today. Follow me to become someone who understands AI.